Sorry for the delay. My Wi-Fi is somewhat unpredictable, which is actually one reason why it works better for me to record these uh, lectures than doing them live. So anyway, let's get back into balancing torus. I'll pick right up where we left off last time. So let M be a right R module, R any ring, and N a left R module. Then the statement of balancing tor is the following. So we want that the left-derived functors of M tensor blank applied to N are isomorphic to left-derived functors of blank tensor N applied to N for all I. So in other words, our two definitions of tor coincide. Okay, so here's the proof. Let P and Q be projective resolutions of M and N, respectively. Then we have a bicomplex, in fact, a first quadrant bicomplex C with CPQ equals PP tensor QQ, and with horizontal differential given by x tensor y maps to d of x tensor y. And vertical differential x tensor y maps to -1 to the p x tensor d of y, where x is in p sub p. So that's where the sign -1 to the p is coming from. So remember that sign is there just to make this a bicomplex. Each square is supposed to anti-commute. So notice that the total complex of this bicomplex C is precisely the tensor product of our two resolutions. Okay, so we have a bicomplex, and it's bounded. In fact, it's concentrated in the first quadrant. So we have two associated spectral sequences given by filtering by columns and filtering by rows. So let's write those down. Oops. Okay, so the first one looks like this. So it's denoted with Roman numeral 1. It has E2 page given by first taking vertical homology and then taking a horizontal homology, and it converges to the homology of tot C. And we have the counterpart spectral sequence, which goes in the opposite order, and it converges to the same thing. Okay, so here's the idea. Both of these spectral sequences, we'll see, collapse to either one row or one column at the second page. But we know that if a spectral sequence collapses to either one row or one column, then we can just read the terms it converges to from that row or that column. But these spectral sequences converge to the same thing. And that's really the idea of the proof. So, okay, so let's do it in detail. Okay, so the first spectral sequence collapses to the 0th row at page 2. So rewriting page 2, we get LP M tensor blank evaluated at n for q equals 0 and 0 otherwise. So if you work it out, that's what the second page ends up looking like. And similarly for the other spectral sequence, so we get LQ blank tensor n evaluated at m in the column p equals 0 and 0 otherwise. So this spectral sequence collapses at the 0th column. Okay, and so as I said before, so by what we know about spectral sequences that collapse to either one row or one column, we can conclude that Ln m tensor blank evaluated at n is isomorphic to Hn of the total complex of C, which in turn is isomorphic to Ln blank tensor n evaluated at m for all n. And that's the proof. That's what we were trying to prove. I'll point out that it follows from the proof that tor n mn computed either way you like, either with the derived functor tensoring on the left or tensoring on the right, is isomorphic to Hn of p tensor q. So that's yet another way to compute tor. Okay, so you might wonder if you can prove a statement about balancing x in the same way that you can prove balancing tor. And I discussed this in some detail in the lecture notes. So the answer is yes, you can, but there's a slight subtlety. So let me explain a little bit. So what about balancing x? So recall, we can define we can define X in two ways. So I'll just suffice it to say we never proved that Ri hom of M blank evaluated at N is isomorphic to Ri hom blank evaluated at N, or blank of N evaluated at M. So this would be the statement of balancing X. Okay, so there is a spectral sequence argument that proves this. So to prove this, the idea is to use the same argument as with Tor, applied to the total complex of a bicomplex built out of hom yeah, I guess I'll say hom p, I guess, let me put it this way. Applied to the complex hom p I, where p is a projective resolution of M, and I is an injective resolution of N. Okay, so this works, but there's a subtlety. The problem is that the associated spectral sequence is unbounded. So the problem is that an injective resolution extends infinitely to the left. And so what we're going to get is a second quadrant spectral sequence. And that won't necessarily be bounded. And so, I mean, we don't even have a definition of convergence for an unbounded spectral sequence. Such a definition exists, we just haven't discussed it. So I wrote this out in detail in the lecture notes, but suffice it to say, if you want to go through the details of proving the balancing of X using a spectral sequence argument, you're going to have to backtrack in Weibel and check out the definition of a convergent unbounded spectral sequence. Anyway, I'll refer you to the lecture notes for details. Okay, so I think it's better to just move on, because I don't want to get too much into unbounded spectral sequences in this class. So I just want to move on to a different example. So here's another nice result using the spectral sequence associated to a bicomplex, a base change for Tor. So theorem. Let F from R to S be a ring map and M a right R module an NA left S module. By the way, I'm noticing a typo in my notes, or just a mistake in my notes. Um, in the statement of base change for Tor, I say right module N, but I mean right module N. Okay, so the statement is there is a spectral sequence with E2 page Tor P of Tor Q R of MS against N, and it converges to Tor P plus Q R of MN. Okay, so let's prove it. So using the machinery we've built up, this is actually pretty easy. So let P be a projective resolution of M over R, and Q a projective resolution of N over S. Then, so we'll form a bicomplex that underlies the tensor product of P and Q, just like with the balancing of Tor argument. So as above, let C be a bicomplex with CPQ equals PP tensor QQ, such that tot C is equal to P tensor Q. Okay, and recall, so we observed earlier that the homology of this total complex coincides with Tor of M against N. So we have a spectral sequence given by taking horizontal and then vertical homology converging to Tor of M against N. Oops. And so it suffices to interpret what this E2 page is. Okay, so let's do that. Okay, so let's first think about what the E1 page is. So E1 is just given by taking a horizontal homology. So E1 is given by HQ of the complex P tensor QP. And now I'm just going to take P tensor R tensor over R with S, tensor over S with QP, so just inserting an S in the middle. Okay, and now we're going to use that QP as projective over S, and therefore it's flat to pull it out of the homology. Okay, so we arrive at that. But we know what this HQ of P tensor R with S is. That's not tot, but tor QR of P of M against S, and then tensor with QP. Okay, so that's the E1 page. And now to get the E2 page, we just need to take vertical homology. And so what we get it's the homology of the complex tor QRMS. So that's just a module, but tensor over S with the resolution Q. But by definition, that's just tor P over S, tor QRMS against N. And that's what we wanted to prove. Okay, so kind of a nice little result there using the spectral sequence associated to a bicomplex. Okay, so we're going to see a few other applications of spectral sequences, but before we do that, we need to develop a little bit more theory. So I'm going to move on to a different topic, which I think is section 5.7 in Weibel. So it's called hyperhomology and hypercohomology. Okay, so basically the idea here is that we somehow want to be able to apply derived functors not just to modules but to complexes. And you might think that's kind of silly because complexes form an abelian category, so why can't I just do the exact same thing? Why can't I just define derived categories or derived functors in the exact same way? But the point is, I want a derived functor that takes complexes and spits out a module, not another complex. Okay, so that's basically the idea. So en route to that goal, I want to make the following definition, which is a sort of special kind of resolution of a complex rather than a module. It's called a Cartan-Eilenberg resolution. Okay, so let's go back to the general setting of an abelian category. So let A be an abelian category with enough projectives. And let C be a complex of objects in A. Then a Cartan-Eilenberg resolution, or rather a left Cartan-Eilenberg resolution of C. I guess I'll give it a name. I'll call it P of C, is an upper half plane bicomplex. So that by that I just mean a bicomplex that's concentrated in the upper half plane. So all of the entries below the x-axis are 0, or not the x-axis, but the p-axis, I guess. Consisting of projective objects in A. So by that I mean all of the entries of the bicomplex are projective, along with a chain map from the bottom row of the bicomplex, namely P star 0 to C, so I'll call that epsilon, satisfying the following. Okay, so let's just take a step back and think about what we're doing here. So I've got a bicomplex of projective objects. It's concentrated in the upper half plane, and the bottom row maps to my complex. Okay, so think of this as like a two-dimensional projective resolution. Okay, so what are the properties that this thing needs to satisfy? Well, first, if one of the entries in my complex happens to be 0, then the entire column above it also has to be 0. So PPQ equals 0 for all Q. Okay? And second, I want this to be a sort of resolution. So how do I encode that property? Well, here's exactly how. So let BP of P with respect to the horizontal differential DH. This is kind of horrendous notation, but it's the notation Weibull uses. So let this denote the boundaries of the horizontal differential DH in P in column P. Okay, so I'm just thinking of one column of the horizontal boundaries in my bicomplex. So you should think of these as lying over the pth entry in our complex C. Okay, so those are the boundaries, and then similarly, HP, PDH denotes the horizontal homology of P in column little p. Okay, so again, so these are, it's just the horizontal homology in position P of my bicomplex. Okay, so you should think of BP and HP as being columns lying over position P in the complex C. Okay, so far all I've done is introduce notation. So what is this requirement? So notice both BP, PDH, and HP, PDH
are complexes with differential dv. It's induced by dv, the vertical differential on the bicomplex. And finally, the requirement is that the map BP of epsilon, the map induced by epsilon from BP PDH to BP of C, and similarly the map induced by epsilon on horizontal homology so the maps are induced by epsilon, but in any case, these maps are projective resolutions. Okay. So that's a mouthful, so let's just circle back and remember what we're doing. Okay, we start with a complex, and we have a bicomplex of projective objects lying above it. And what we're saying is that each column isn't exactly a projective resolution of the component in C, but if we pass to boundaries, horizontal boundaries, oh, good God, what is this? I have no idea what this is. Well, anyway, I don't know why this AT&T ad is showing up on my laptop, but so we're not getting projective resolutions of the components of C, but we're getting projective resolutions of the homology and the boundaries in C. That's the idea. Okay, so we'll continue with a discussion of Cartan-Eilenberg resolutions next time, and in particular, we'll show that Cartan-Eilenberg resolutions always exist. Okay. Okay, talk to you Wednesday.